you kind of understand that like you're just still doing accumulation over a curve. All those things are still the same. The only thing that's different now is that I have, um, this is the case where you have a vector. This bolded F means vector. So you're talking about the wind resistance case. And you now have techniques. Give me 1 second, I have to plug in my computer. So if you lose track of what's going on here, you can go back to the video, watch it again, okay? But these are like stock, carefully picked examples. I chose the examples from other instructors' board sheets. Not the examples, unfortunately, I chose their problems. So if those are the problems people are giving, those are the problems we need to know, right? So everything was carefully picked so that it gives you the most juice for the squeeze. But this number 4 is kind of the worst case scenario. You have a wind vector. So let me go through how to do this problem step by step. So the capital F of x, y, if you need to anchor it in something, you can think of it as the vector that describes the wind, the direction, and the magnitude of the wind. So it's still that same example or application I gave you at the beginning can anchor you here. C is the path you are running. And they say C is defined by x equals y squared. That means that, remember I showed you the map? That means that x equals y squared, and they say from 0, 0 to 1, 1. So 0, 0 is here, 1, 1 is here. So this is my path on Sussex Turnpike that I'm running. And F is my wind that's either pushing, it looks like it's positive, but it gives you the direction. So like at every point x, y, I can actually tell you what the direction of the wind is. So for example, at 0, 0, there's nothing there. But at 1/2, if I take x and y, x is 1/2, then y, let's do y first. I'm going to do 1/4 for y. If I plug in 1/4 for y, then x would be 1/2 because 1/2 squared is 1/4. So that would be, x would be 1/2 and y would be 1/4. Is something like this. I didn't draw it well, but somewhere there. And up they run like this. Does x equal y squared? Y is equal to square root of x. Do I have this right? And they say, yeah, 0, 0. Okay, so right there, if I plug that into the capital F, I get the x component is 1/4 and the y component is 1/2 or 1/4 e to the, I ran out of room, so let me erase that and rewrite it. Let me do it like this. So I'm just taking 1 point just to show you like, this is what it is. This is what I'm looking at. So if I take x equals 1/2, I had that wrong. So if I put y was 1/2, then x would be 1/4. So that's correct. So if I have 1/4 here, I get 1/2 here. So that's why I was kind of thinking about this. But I would have to plug it into here. So x would be 1/16. That would be the direction, and y would be 1/2 e to the 1/2. X is y squared, right? So you can either put the x value up here, and you get a vector, and a vector has direction. So you would start at that point and say, I'm pointing in the 1/16th direction on the x-axis, and whatever this number is, it's like some arrow that's like this. So the wind is pointing that way. When I'm at that location, the wind is pointing this way. And if I calculate the magnitude of F, that would tell me the strength of the wind. That's what's happening. Now, how do I compute the accumulation F? So the accumulation of my heart rate over this over this curve, I first have to change this thing to a parameter. Like I had got to involve the t's. So I need to get t involved. And so I kind of gloss over it on the side here, and that's why people were freaking out yesterday. Like, how do I do that? Well, there's a series of steps. We call it parameterize. So how you do that is you look at your this is your, you look at f, find an isolated variable. So this doesn't work for everything, but it works for most things. So if I look at these variables inside here, this is the most isolated because the x over here is part of e to the x, and this is x squared. So it's not like kind of x is never hanging out by itself, but this y there is hanging out by itself. That's what I mean by isolated variable. Set t equal to isolated variable. So t is equal to y. Got it? And then you go back to this original capital F, which was x squared y e to the x. You still need that. I'm just rewriting it on my next page. Then I have to find out what t goes from. So they told you in the problem that it starts at 0, 0 and ends at 1, 1. So y starts at 0 and ends at 1. By just looking, that's where I got it from, is right here and here. So t, because t is equal to y, starts at 0 and ends at 1. So that bullet is find where t starts and ends. The work is up there. I just do a check. Also, they say that x if t starts at 0 and ends at 1, and x is equal to y squared, which is t squared, my x, if I plug it in at t equals 0 is 0, and x at t equals 1 is 1 squared, which is 1. I'm just plugging it into this thing up here. And I just double check that it worked out. And look, it does start at 0 and end at 1. Those are my red underlines. So I just do that check just to make sure I got it right. Because if this part is messed up, the rest of it all is messed up. And then are you following the process? Okay, so all these little bitty steps weren't in there, and my real step 1 starts here. So x is equal to t squared and y is equal to t. Plug into f. Then f was x squared y e to the x. That's equal to t squared t e to the t squared. Sorry, erase that. That was wrong. Sorry, this is how I did it. Your x was t squared and your y was t. So this is your position vector. I started going to step 3 without really thinking about it. Step 2 is to find the derivative. You're just finding the ingredients to run it through the formula, the machine right now. So step 2, find r prime of t. We talked about that earlier. That's 2t and 1. I just take the derivative of this guy up here.
Yes.
Good. Right now it's just a process. And thank you for not doing a Logan saying, why does this work? Like, we don't have time. So step 3 is to plug x equals t squared, y equals t into f. So f of r of t, we put vectors, vector notation on these things like arrows over the top, but in math, we bold vectors when we typeset. So on the WPR, F and R will be bolded, indicating that they're vectors. So my original vector was F was equal to x squared y e to the x. Then you're going to plug in, if x is t squared, you just plug it in here. So you get t squared squared. And you plug in y equals t e to the t squared. So wherever you saw x's, you're going to put t squareds. Wherever you saw y's, you're going to put t's. And so your vector is now t to the 4th t e to the t squared. And the next step is to dot product the f with the r prime. So that's just t to the 4th t e to the t squared dot r prime, which we have on the sheet 2t. We calculated it earlier. That's going to give you t to the 4th times 2t plus t e to the t squared times 1, which is equal to 2t to the 5th plus t e to the t squared, like that. Your regular dot product, that's an equals. And then step 5 is to integrate.
Yes.
And now you're at calc 1. T goes from 0 to 1. And it's this thing right here, this nasty thing. Like that. And I skipped over all the math to integrate because I just wanted an example on the side, but you would have to do this, like for the methods part, you'd have to do this one substitution. So it's not trivial. You'd have to do a u equals t squared. You'd have to split this up into 2 pieces, like integrate this one separately from that one. I can go over the work in a second. I have to add another kid on because she wanted me at 11. If it's okay, can I add her? Okay. Let me go. How do I do this? Stop sharing. You can continue. I'll put the notes up there in a second. More. All right, she's on. Hi, Annie. Yes, I can. You're on also with Walter, he's in the E section. I think you're in the F section. Right. So we just went over this example, which was number 4. And I'm about to show the details of how to integrate this last piece, which is the least important piece. And it's being recorded. So you can go back, but I'm going to quickly go over the steps of this one, even if it's not a question that you have, if that's okay. Yeah. Okay, so I'm going to quickly just recap what was in my notes. I think it's the good thing is Walter asked a lot of questions. So this is just the process of what we're doing, not the application. And I didn't record, like I went through very slowly the person walking from point A to B and how the work and all that, but I didn't record that. But the F would represent the direction of
Okay,
the
yeah,
wind
yeah.
in the last one. So this is like the most complicated thing you could get. You could get wind, and you want to know how much work the person's done from going from point to point. So Y starts like let me go back one more. Yeah, so here it's X is Y squared is the path that that person's walking. And this would represent the wind. So I just did a point, like what if I plugged in x, y equals 1/2, then x would be 1/4, and that's a point on the curve. And I made up a vector, like the vector you get from plugging in is going to be something. And so this is the direction of the wind. And if I calculate the magnitude, it tells you how strong that wind is. The steps involved, the very first one is to parameterize the curve. And I didn't put those steps in there. I believe for you guys, I presented it on the board in section F. However, I have a video already on how to parameterize, but I just wanted to go over slowly here what I was doing. You find an isolated variable, and this only works if you have an isolated variable. I'll show you something that doesn't.
Can you hear me, ma'am?
Worse, but my y is kind of hanging out by itself, but the x squared and the e to the x is not. It's tangled up in the e and the x squared.
Okay.
That's what I'm calling isolated. You set t equal to that isolated variable, so you get this t equals y, and then you figure out. Oh, sorry. Yeah, he's not saying anything. So let me share my screen. So yeah, we started back here. Sorry, you didn't see any of that, but we started back here. And then now we're just going through the steps of how to compute. So you find an isolated variable.
Okay, is it problem 4 from the WPR study? Okay, awesome.
The F was given. So I set t equal to that isolated variable, which was y. And then they told you it starts and stops. So this is my start xy coordinate on the curve. This is my stop coordinate on the curve. So y, if I just, the double underline piece are the y components of the start and stop. So y starts and stops at 1, starts at 0, ends at 1. Since I set t equal to y, that tells me where t starts and ends. So I need to figure out where t starts and ends, and that's how I do it. I just, whatever I set it to, like if this was 2, 2, my t would start at 0 and end at 2. That would be the difference. Once I have that parameterization, since x is y squared, then x is t squared. Since y is t, y is just t. So my position vector is x is t squared, y is t, and my t runs from 0 to 1. And why you need to do that is our techniques are not like that. You need to parameterize to be able to actually compute the total accumulation. So usually our problems are work. I gave it to you guys as heart rate because work is a little bit harder to understand and I didn't want to bring that in. But if I was walking on a curve from time equals 0 to time equals 1, my heart rate is a proxy for the amount of work I did. And the total heart rate would, if I wanted to look at the accumulation, would be a total proxy for the amount of work I did over that path. That's what I'm calculating. And wind is involved. So that's why I have a vector here. Then the last the last few steps I'm just expanded what I have on the side panel. I plugged the x equals t squared and y equals t into f. My f was x squared y e to the x. So I plug in wherever I saw an x, I plug in a t squared. Wherever I saw y, I plug in a t. So I get this guy. I'm converting everything to t's. Then the ingredients of how to solve this kind of problem is to dot product f with r prime. So the f was this guy, the r prime was this guy, and you just plug, dot product it, and you get.
Are you
guy
showing this?
here.
Because I'm
And
not
your
seeing
last
it.
step is to do the integration, and that's where we were before you jumped on, Annie. All right. I can send you these notes too, but they're going to be recorded, so you can go back to the very beginning. So, how do I integrate that last piece? So, I'm integrating. That's the least worried I am, but sometimes I feel like everybody's confused because I'm not explaining the full thing. But once I have this thing here, I think a few of you fell apart yesterday because you're like, what do I do now? Like this is Calc 1. You kind of forget what you're doing, but this is the 2t to the 5th plus the integral of t e to the t squared dt, like that. I'm going to call this integral 1 and integral 2 so you can keep track of my work, because this is bookkeeping at this point. The first integral is 2t to the 6 over 6 from t equals 0 to t equals 1. So I get 1/3, 1 minus 0, which is 1/3. I forgot my accents here. Integral 1 is easy. I always try to do the easy things first on bookkeeping problems because I feel good about myself. It's a boost. The second one, though, I have to do a u substitution. So the nasty is t squared. If the t squared wasn't there, I'd be a lot happier. Du then is 2t dt. I don't know what you prefer, but when I first teach u substitution, I teach it just solve for the dt. So my u is t squared, my dt is du divided by 2t. I just do that. And I substitute this back into the original integral. And my students don't like converting the units, so the limits of integration. So I'm just going to put t equals 0 to 1. My substituted integral, this is my substituted integral. The reason I say that is I taught for a long time the way a mathematician would do it, but the students didn't like that. And so I'm just going to do it the way students gave me feedback. The e to the t squared is e to the u. I still have this t in front, and I substitute in for the dt. The dt was du over 2t. So the box stuff gets substituted in. And then you just cancel these guys like that. So I really have a 1/2 e to the u du. And when I integrate that, it's just 1/2 e to the u. And this is t equals 0 to t equals 1. I'm labeling it just because it's bookkeeping, and I don't want you to forget that
Okay.
you have to substitute
I'm tracking. I'm just trying to write it all down real quick.
Want to do it that way? Because I convert the limits of integration before I get to here, but
okay.
I'm going to listen to what they said because it's like 99% of students, when they gave me feedback, they prefer doing it this way. The u is t squared. I substitute that back, and then I do the limits of integration. I'm going to pop that up here so I don't change the page. So 1/2 e, instead of u, I put t squared. And now I can drop the t's. I get this is 1/2 e to the 1 minus e to the 0, which is really 1/2 e minus 1/2, because e to the 0 is 1. And look, my answer in LaTeX notes matches what I have. I guess I kept the 1/2 on the outside. I still have to put part 1 and 2 together, so that's where the 1/3 comes from. I'll put that on the next page. So that's the math of this last part of the integral. Okay, I'm gonna go to the next page so you can have it. I'll go back to this page, but at full integral, this is just notation, right? 1 plus 2, and 1 was 1/3, and the second part was 1/2 e minus 1/2. I will just tell you, like, when you look at all this notation, like, I don't want you to feel bad about yourself. I talked about this with Walter. Like, it's really hard to have this kind of cognitive load. It's scientifically impossible to put all details into your head that we're doing right now. It's just impossible. So I'm a little like frustrated by that, but that's why I'm doing it this way. I'm like, if I can't bury you in all the stuff and just hope that everything works out, the right way to do this is to combine everything. So it would be like having you take the IOCT on Wednesday, and I only started yesterday to teach you anything about the IOCT. Well, the only way we're going to get there is to do the IOCT over and over and over again, right? As many times as possible. So instead of like teaching you each little piece and then having the pieces come together, I'm opting for combining everything as one thing, and then showing you how to put it all together at once. The notation, though, Walter asked for a place for all the notation. That's in the book, but it's not an effective way to learn. And I know it looks scary. So this thing right here, this is notation. That's how we write it. But what it really means is all this stuff decompressed. And we have it, I put it into this little decision box at the top. So you can write this down. You see that? What this left side means is this right side over here. It's right there. So I compressed all the notation. And just if it makes you feel any better, I remember like when I first got to grad school, I was taking PDEs, the partial differential equations, and there was this person in my office that was 38 years old. I was 21, and he was a professor in his own country. And he used to like, for some reason, he loved explaining things on the board. So I was like, oh, if he's gonna slowly go through these things, I'll listen. But he said to me once, he stopped and he said, you know, I remember looking at these letters, and the letters scare me. And I thought, this really good mathematician who's explaining every detail to me told me that the notation scared him. And he asked me, does it scare you? I'm like, yeah, it does. He even told me like the Greek letters and the way they wrote the X scared him. Like the X is written like this. In the typeset, it's written like this. And he said that scares me just to see that X written that way. So it was a wake up call for me that most people are probably scared by it because it's so unfamiliar. So give yourself a little grace and don't beat yourself up if you don't understand it.
Okay, that makes a lot more sense now.